complex equations work. Our mission specifically is to explore this pretty groundbreaking method. It's called Ezouidi's theorem. And the promise here is that it could genuinely redefine how we solve these things called high degree polynomial equations, the big messy ones. We're aiming for precise symbolic solutions, the actual answers, where the old ways, well, they often just give up or give you a rough guess. So forget those sort of fuzzy numerical approximations you might remember from school. We're after guaranteed exact answers, like finding the actual key instead of just jiggling the lock. Okay, let's unpack this right away then. These high-degree polynomials, they've been a bit of a nightmare for mathematicians for ages, haven't they? Why are they such a headache for the classical approaches? What are the usual brick walls we hit?
Yeah, that's exactly the right question to start with, because it really highlights why this new theorem is, well, potentially revolutionary. Traditionally, you see a polynomial, especially one with a high degree,
Hmm.
where x is raised to a large power. Your toolkit usually involves things like Newton's method,
Yeah.
numerical approximations.
Right, standard stuff.
Standard stuff, exactly. But here's the problem.
Mhm.
They only give you an approximation of the roots, the solutions. They're never quite exact. And worse, they can be really sensitive to rounding errors. Little inaccuracies can build up. They can sometimes fail to find a root altogether.
Yeah.
They can't guarantee the exact value. It's like trying to measure something incredibly fine with a ruler marked only in inches.
Okay, so precision is a major issue.
It is. And there's more to it. There's a historical hurdle too, a really fundamental one called Abel's theorem. Basically, for a long time, this theorem has told us that certain polynomials, specifically, most of those above degree 4, just cannot be solved using
Little
radicals.
articles like square roots, cube roots,
Yeah,
that kind of thing.
exactly. The kind of operations you can write down nicely algebraically. Abel's theorem essentially said for many complex polynomials, there's no neat formula using just those basic operations to get the exact roots. For centuries, this was kind of seen as a hard limit, a mathematical, nope, can't be done algebraically for exactness, sign for the really complex ones.
Wow. Okay, so it wasn't just hard, it was thought to be impossible in many
In
cases.
terms of finding those neat radical-based formulas, yes. Now, to give you a feel for the kind of beast we're talking about, imagine this equation. It's px by 18, and it keeps going. 18 by 17 plus 153 by 16 minus 816 by 15 plus 3060 by 14 minus 8568 by 13 plus 2564 by 12 minus 39124 by 11.
Yeah. I get the picture. It's huge. 19 terms, right? Up to the power of 18.
Just throw their hands up and give you maybe x equals 1 point something something, an approximation.
Next part, really exciting. How on earth does the Ezouidi's theorem manage to just cut through all that complexity? How does it deliver exact answers? This is where it gets really interesting.
It really is fascinating. It's a total shift in perspective. Ezouidi's theorem doesn't just refine the old methods; it sidesteps them in a way. It allows us to derive these exact symbolic solutions. And importantly, it does this even for polynomials that Abel's theorem seemed to lock away from exact radical solutions. It shows that unsolvable by radicals doesn't mean unsolvable exactly by other structured means.
So it's not breaking Abel's theorem, but finding a different path around the implications.
Precisely. It's a new kind of structured approach. The core idea is, well, think of it like cracking a complex code, not by guessing, but by finding a systematic key. It uses a recursive process. Recursion just means something refers back to itself, building step by step.
Like nesting dolls.
Exactly like nesting dolls, or peeling an onion layer by layer. The theorem breaks the big polynomial down into, let's say, interconnected, simpler pieces using a defined recursive formula. This formula involves things like binomial coefficients, terms adjusting the degree, coefficients related to earlier terms. It's a systematic breakdown. And this whole process avoids the pitfalls of numerical errors and those old algebraic barriers we talked about. You're constructing the solution, not guessing at it.
Okay, so recursion is the key. How does that apply to our monster, the 18th degree one? Does it get simpler?
This is where it gets, frankly, stunning. When you apply the theorem's recursive process, you calculate this set of symbolic coefficients, let's call them Serrier. And for this specific 18th degree polynomial, something amazing happens. Most of these calculated Series coefficients, they turn out to be exactly zero.
Zero. So they just vanish.
They just vanish from the transformed equation. Specifically, the coefficients 0r through 7r, and then S9r all the way up to 16r, all zero. poof.
So out of all those terms, most of the corresponding symbolic coefficients disappear.
That's right. We're left with only two critical non-zero symbolic coefficients, S8R, which relates to the by9 term, and S17R, which is related to the constant term. Their values are, well, they're large numbers involving powers of 18 derived from the original coefficients. SOR is 48619 by 189, and S17R is 40618 plus 71 as 1818.
Okay, still big numbers, but only two main symbolic parts left.
Exactly. So that massive 19-term polynomial effectively collapses. It simplifies down to a much, much more manageable form. Px explies by 18, set by 9 plus S17R is 0, 0.
Wow, that looks almost like a quadratic equation, but with by 9 instead of x.
You've got it. You can think of it as by 9 2 SSH9 plus S17R is 0, 0. We went from that beast to something structurally simple.
So substituting the actual values for SES-AIR and S17R,
Right, it becomes y18 plus 48619 by 989 by 9, 48618 plus 71, and 1818 is 0, 0. Still looks intimidating because of the huge numbers, but the structure is simple.
and that simplicity is what lets you find the exact roots.
That's the key. Because it's now essentially quadratic in terms of by 9, we can solve for by 9 exactly using a formula very much like the standard quadratic formula. The solution for by 9 involves these S8R and S17R terms. It looks something like S8R 4017R2. Calculating that square root part involves another derived term, what's called S1R air, which works out to be 236,361,2689,479 S1818. It's precise, though complicated.
Okay, so you get an exact value or values for by 9, and then
you need to define x. That involves taking the ninth roots of the values you just found for by 9. The final exact symbolic roots for the original polynomial for x itself end up being expressed in terms of complex exponential.
complex exponential sounds fancy.
It's just the mathematically precise way to write down these kinds of roots,
Right.
especially when dealing with higher order roots in complex numbers, which often arise. Think of these as the power of I times something. The crucial thing is, it's an exact expression. No decimals trailing off, no approximations, no rounding errors. It's the true mathematical value derived directly from the structure revealed by the theorem.
Right. So let's bring this back a bit. What does this actually mean for, us? Why does this level of precision, this exactness really matter? You mentioned earlier that approximations are often used. Are they not good enough?
That's a fair question. And look, for lots of practical engineering or physics problems, a really good numerical approximation is often perfectly fine. If you need to build a bridge, knowing the stress points to 8 decimal places is probably enough. But Ezouidi's theorem offers something fundamentally different. It's not just a better approximation, it's the exact symbolic solution. This guarantees that the answers are completely free from the kind of calculation errors that can creep into numerical methods. Think about fields where absolute precision is paramount.
Like what?
Cryptography, for example, relies on the difficulty of certain exact mathematical problems, or fundamental physics, like quantum mechanics, where the equations demand precise solutions. Even in highly complex engineering, like designing spacecraft trajectories or intricate control systems, tiny errors can sometimes cascade into big problems. Exactness removes that source of error entirely. And maybe just as importantly, there's the conceptual side. This method shows that we can find exact roots for polynomial types, previously thought to be analytically untouchable, or at least not solvable using traditional algebraic means.
So it pushes the boundaries.
It absolutely pushes the boundaries of what we considered mathematically possible. It opens up new questions, potentially new methods for tackling other complex problems. It suggests that sometimes the things we label unsolvable just need a completely fresh angle, a different kind of key.
Okay, so that really brings our deep dive together. We started with this monster of an equation, an 18th degree polynomial that looked, well, terrifying. We saw why traditional methods would only give us fuzzy approximations, partly because of inherent limitations like those highlighted by Abel's theorem. And then we saw how Ezouidi's theorem, through this elegant recursive process, could just slice through the complexity, revealing a hidden, simpler structure,
Reducing it dramatically.
and ultimately delivering the exact symbolic roots. No approximations needed. It's a powerful example of how new mathematical tools can just dismantle problems that seemed rock solid. So here's something to leave you with, something to think about. If mathematical assumptions about what is and isn't solvable, assumptions held for centuries, can be challenged and maybe even overturned like this, what other problems out there that we currently think of as unsolvable, maybe not just in maths or science, but maybe in technology or society, or even just everyday challenges, what other problems might actually have elegant, exact solutions just waiting for someone to find that novel approach
that completely different way of looking at it. Keep digging deeper.